right? Now there's reasons for this, and the reason is simply that in the case of chromium, elemental chromium, this is again kind of Hund's rule, having maximum spin multiplicity results in stability. You have half, and the other reason is maybe a little bit more correct, half-fold orbitals result in more stability. Right? That's why it goes for that electron configuration. And in the case of copper, it promotes one electron from the 4s into the 3d, because then it ends up with a completely full d shell, right, which is also more stable than a, let's say, half empty, or one that's missing one electron. So copper and chromium are exceptions. There are other exceptions as well. I don't expect you to memorize them. But copper and chromium certainly I expect you to know as exceptions to the Aufbau principle.
And can it work with like metals too? Like if we have like, just to have more...
P metals don't have any P block, you mean S block metals? Or?
Yeah, I mean, the same way we have like chromium that fills at 4s and then the 3d
no.
just to...
This doesn't happen very often, right? I mean, I should just tell you, these exceptions happen quite rarely. But no, it doesn't happen for the P block elements. No, it doesn't. Yes.
So if I remember right correctly, I think it was like for that first S orbital, they take away the S electron at the end of the next orbital, specifically to make that last one more stable.
Correct.
But I can't remember why.
Because if we let's consider the alternative, right? For copper, if I first obey the Aufbau principle, then I should have 2 electrons in the 4s, which means I would then have only 9 electrons in the 3d. Now that's okay, but having a full shell is more stable, because then you have all orbitals completely paired up. So either half-fold or completely fold results in higher stability. Okay. All right, so this is the electron configuration for the transition metals, the 3D transition metals. Now let's look at writing down some electron configurations. Suppose I were to ask you to write down the electron configuration of chromium 3+. Right, how would we do that? Chromium 3+. Now what does 3+ mean? It means it's an ion. It means that I've taken out how many electrons? 3. Now the electron configuration of elemental chromium, chromium 0, right, is shown here. See, I've used noble gas notation. So what would be the electron configuration of chromium 3+?
Maybe argon, and then we'll put one of the electrons in the 4s. So we have a 4s2 and 3d minus 3, so 2.
Okay, now? Yes?
4s2, 3d1.
4s2, 3d1. Okay, now, all right, so anyone else want to venture against? That's also incorrect.
We take away from the P shell?
From the?
From the P shell of the previous...
No. We take away from the highest principal energy level first. Again, this is counterintuitive, because you would think, why would you do that? The 3D is higher in energy, so you should start taking electrons out of the 3D first. It turns out you don't. You take the electrons out of the 4th shell first because it's got a higher quantum number. So I'm going to empty out the 4 first and then start emptying out the 3. So if I need to get rid of 3 electrons, what am I going to do? I'm going to take 1 electron out of the 4s and 2 out of the 3d, and the electron configuration is simply going to be 3d3. Let's do another example, titanium 2+. Titanium 2+. So what you've got to do if you do this is you've got to write down the electron configuration of the element in its 0 oxidation state, then start taking out electrons. So there's titanium 0. So what will be the electron configuration of titanium 2+? Yes?
3d2?
Correct. It's going to be not 3d2, it's going to be argon, don't forget noble gas configuration, 3d2. Because I empty out the 4th energy shell first, then the 3rd, then the 3d. Right, so this is important. You should be able to do this, and you should be able to write down electron configurations. Okay. So now let's go on. Let's soldier on. Let's soldier on. Well, this is just the examples that I've done. Well, I did titanium 4+. Incidentally, what would titanium 4 plus be? Just argon, right? You've taken everything out. Okay. Now, I don't want to digress, but I'm an inorganic chemist, and if you work with complexes, iron, for example, what happens if you actually make a complex out of this thing, if you take these elements and you put like ligands on them and make compounds with them, what actually happens is, and I don't want to confuse you guys, but I'll just tell you from the Departments of Useless Information, that the 2 electrons in the 4th energy level get promoted into the 3D. So iron 0 is actually D8. Cobalt is there's a mistake here, right? That should be that's not D6, right? But iron would be D8, scandium would be D3, titanium would be D4, and so on. Vanadium D5, chromium D6, manganese D7. So what happens in reality is that those 2 electrons don't sit in the 4s, they get promoted into the 3D. Reason why is because they're then used to form bonds to things that then bind to the metal. But for the purposes of this course, we deal with monoatomic entities, so we don't promote the electrons in that way. This, of course, should be D7, D8, D9. So yeah, there's a mistake here, right? But anyway, okay. So that's the story for electron configurations. Now, okay, I've already done that. My last comment on this is just the notion of para and diamagnetic stuff. Now, if you take something that has a species or an element or a compound that has unpaired electrons, remember I said unpaired electrons are like little magnets generating magnetic fields. If you have unpaired electrons in a compound, what's going to happen? Well, what's going to happen is if you expose that compound to a magnetic field, it's going to interact with a magnetic field. And depending on the degree of interaction, you can actually determine the number of unpaired electrons in a compound or in an atom, in a sample. This is basically what you do. We call this magnetometry, and this is actually a Gouy balance. This is a very simple way of doing it. You put a sample in a magnetic field, and you sort of weigh it and see how the mass changes. If the mass changes, it means it's interacting with a magnetic field. It means it's unpaired electrons. And the degree of the interaction or the mass change you can then relate to the number of unpaired electrons. And you can experimentally determine how many unpaired electrons there are. That comes back to your question as well. You can do magnetometry to figure these things out. This is a simple way of doing it. There are more sophisticated ways of doing it. And magnetometry is in its own right a blossoming science. And yeah, very important again in inorganic chemistry. If you want to understand what the electron sort of distribution is in a compound, you need to do this sort of stuff. But for you, what's important is knowing paramagnetic means unpaired electrons, diamagnetic means that all the orbitals have 2 electrons, there's no unpaired electrons. And of course, if all the orbitals have 2 electrons, one spin up and one spin down, there's going to be no net magnetic field, isn't it? Because they're all paired up. Right. So that's that. And if you want to learn more about that, you should take my course in the fall. Okay. Now we're going to move on to the next topic. So that's now atomic structure done and dusted. You know, now we're going to move on to Lewis structures. What is that all about? This is exceptionally important. I can't stress that enough. We're going to talk about all these things now, and we're going to sort of, in the last hour, do Lewis theory and VSEPR theory. Now, I'd like to just say one thing again. We have a task devoted to this VSEPR theory as well, because this is very, very important for future chemistry studies. Totally important. Now, what is the Lewis structure? What is Lewis theory? Lewis was an American chemist, and he was really the father of this. That's why we call it a Lewis structure, Gilbert Lewis. He said, well, you know, if you want to discuss bonding between atoms, really and we've sort of discussed this already in one of the tasks, it is the interaction of valence electrons. It's that simple. The electrons in the outer shell. The other electrons do not play a role in that. and you can really distinguish two types of bonds, ionic and covalent bonds. Ionic bonds are bonds where you have a very big difference in the electronegativity between the two atoms, and with covalent bonds, the difference is less significant, okay? And atoms, what he said, are going to try to do something called achieve noble gas configuration. In other words, have 8 electrons around them, shared or not shared. And that's the principle behind this. Now, we can write Lewis symbols. We call them Lewis symbols for the elements. Is essentially the chemical symbol of the elements and the number of unpaired electrons. So silicon we find in the 4th group, right? So it's got 4 valence electrons. Oxygen is in group 6. It has 6 valence electrons, and I can represent these electrons as dots. Iodine is in group 7. It has 7 valence electrons. So these dots represent the valence electrons which Lewis said are going to participate in bonding. Okay? And again, this you get from the periodic table. A magic periodic table is so beautifully and elegantly structured. You simply look at the group number, and that gives you the number of valence electrons. It's that simple. Nitrogen is in group 5, phosphorus is in group 5. It has 5 valence electrons, which we can depict in that way. Now, what if I want to form a chemical bond between two elements? Well, we draw. This is now the simplest Lewis structure you can imagine as dihydrogen. I take 2 hydrogen atoms. Each hydrogen atom has 1 valence electron. I bring them together, and what are they going to do? They're going to share. They're going to share with each other, right? They're going to share with each other, and they're going to form a chemical bond. Now we can represent it like that or like that. Both of these are called Lewis structures. Okay. Nowadays, when I was a student, we used to call that a Lewis structure, and that we used to call a Cooper structure. Nowadays, people say, oh, well, they're just Lewis structures, right? So you can draw a Lewis structure either like that or like that. Both of these are acceptable, right? But strictly speaking, that's a Lewis structure, a Lewis dot structure. But I'll accept both. This is much easier to draw. Let's think about chlorine. Diatomic, if you take a diatomic chlorine gas, each chlorine atom has how many valence electrons? 7. Why? Because it's in group 7, the noble gases. And if I want to bring them together in a way so as I achieve noble gas configuration, I have to form a chemical bond between the 2 chlorine atoms, share this unpaired electron, and again I can represent it like this or like this. These are both Lewis structures in 2018. And this line means that it's a chemical bond, a covalent bond, and I get 2 types of electron pairs, right? Bonding pairs and lone pairs. This is a bonding pair, and these electrons that are stuck on the chlorine atom here, which are not participating in bonding, we call lone pairs. And I think the name is very sort of descriptive. They're lonely. You know, they're sitting there in an orbital on the chlorine atom and sort of just looking at each other. They're not doing anything, right? They're lone pairs. Lone pairs are electron pairs that are not involved in bonding. This is going to become very important later. Lone pairs and bonding pairs when we get to the SEPR theory. But what I want you to understand now is if we want to draw a Lewis structure, we have to do it in such a way that we try to get each atom to have 8 electrons around it. Okay? This would be the Lewis structure of water. Now what are we doing here? We're marrying oxygen with 6 valence electrons with 2 hydrogen atoms. Okay? And each hydrogen atom has 1 unpaired electron. And remember, oxygen is wanting to have 8 valence electrons around it all, the octet configuration. Hydrogen doesn't have the octet configuration because it only has an s orbital, okay? But most other elements do. And this would be the Lewis structure of water. 2 bonding pairs between oxygen and hydrogen and 2 lone pairs. There you see them. That is the Lewis structure of water, which of course we can represent the bonding pairs with lines if we so wish. Okay, this would be the Lewis structure of methanol. Okay, now here are some guiding principles. So if I give you a formula, the question is which atom goes in the middle and which goes on the side. These are some guiding principles. Okay, hydrogen's always terminal atoms. Central atoms are those with the lowest electronegativity. Like this is going to become important later on. And carbon atoms are generally always central atoms, and generally structures are compact and symmetrical. What that basically means is you're not going to put the atoms in a long line next to each other. You're going to try and sort of pack them around the central atom as far as possible. So these are just some guiding principles to drawing Lewis structures. We're going to practice and practice and practice until it comes out of your ears, okay? Because by the end of this course, everyone in this class is going to be able to draw Lewis structures. That's very important. Now, here are some more guiding principles to drawing Lewis structures, which I'm not really going to go over. This is something that you can sort of look at. I draw Lewis structures in a way that it's like playing a game, and we're going to look at that in a minute, because I think it's much more intuitive. But I put this here for those of you that struggle with Lewis structures to just guide you. Some students like an algorithm. Okay, do this, then do that. I've never liked that. I do Lewis structures in a more intuitive way. We're going to do some examples after the break. Before we get to the break, I just want to look at two further examples. Carbon dioxide, right, the evil greenhouse gas. If I want to draw the Lewis structure, what do I have to do? Well, remember the rule, the most electropositive element goes in the middle, which is carbon. Carbon is more electropositive, less electronegative than oxygen. And the oxygen atoms go on the side. Now the question is, I want to get 8 electrons around each of those atoms. How am I going to do it? Well, I have to marry unpaired electrons with unpaired electrons. Now, this is what I mean by doing things in an intuitive way. I put it down on paper and I start playing around with a structure. I start marrying up unpaired electrons and I get something like this. So just ignore what's going on down here. Let's say I'm doing this in an intuitive way, carbon and oxygen, and I'm marrying up unpaired electrons. I get this guy here. This is what I get while I'm playing, right? Is that a reasonable Lewis structure for carbon dioxide? No, why not?
Because
there's unpaired electrons, which is that's a point. Well, not necessarily, but okay, yes, you're right. On the oxygen atoms, there's unpaired electrons, so that typically means unstable because it's a radical. Right. What else?
None of the atoms fulfill the octet.
Sorry?
None of the atoms fulfill the octet.
Correct, very good. This carbon atom only has 6 electrons around it. That violates the octet rule. And this guy as well. So that's no good. So how do I remedy that situation? Well, I take that and I marry these unpaired electrons together, right? There's 2 unpaired electrons here and there's 2 unpaired electrons there. And what I end up with is a Lewis structure that looks like that, where I've got double bonds. And that is an acceptable Lewis structure for carbon dioxide. And in fact, the correct Lewis structure. I bet most people that are writing articles about carbon dioxide and being an evil greenhouse gas do not know the Lewis structure of carbon dioxide. And you do, right? So after today, you know the Lewis structure. What about nitrogen? If I want to bring 2 nitrogen atoms together, again, you see how I do it intuitively. I just put the 2 nitrogen atoms down with all the electrons, with this Lewis notation, and I start moving electrons around intuitively until I arrive at something that is acceptable, something that has 8 valence electrons around each atom, and I'm happy. Why? Because that we fulfilled the octet rule. Interestingly, nitrogen has triple bonds between the 2 atoms, okay? And I think we're now going to take a 5-minute break, okay? Is that okay? Mm-hmm. Is everyone okay? Do we need a therapy session?
Not yet.
All right, well, I'll be back in 5 minutes, okay?
Share the what? So even though they have AIDS, they're sharing some of their AIDS with the other ones, so that the other one can say, as long as you're having a hard time sharing you? No, I'm not going to go there. I don't know. But then I thought about it when you see it. Juliana was. Right now I'm doing
Oh, yeah. Used to have them around themselves or shared with others.
She came in.
Yeah, but
Juliana. But here, like Juliana said her order and get up and leave the house before. Yeah. But I was just like, I need to go to the exact same place, exact same time.
Like if you have like shapes, if you have like a
Yeah, I still don't understand. I still don't understand.
no, I
It's pretty good at explaining. Yeah, it's fast, but I think
exactly. So you'll eventually
you don't. I understand the concept of order. Yeah, I think the best way is to get it. It still makes sense from them. So you have like 1S2. This is just this in the first, and then the next one's gonna have A, right?
Yeah.
So then 2, it's gonna have A, so it's got 2, and it's got 6, which is 8. So 2 is 8.
This is P.
Yeah, but S and B are subletters.
Like 3.
Yeah, it's kind of like so. You've got your nucleus, and then you've got first shell has got like subletters, right? And the second one, so like shell
Question.
have subletters. That's basically what
Did you understand this part, the why
energy
we
levels
take
so all the electrons.